Let's talk about that smartwatch on your wrist. Yeah, we all know it's great for tracking steps, but what if it could do so much more? What if it could unlock some pretty deep secrets about your health, just by paying attention to the way you walk? Well, today we're diving into some incredible new research that's making that a reality.
Seriously, forget about just counting steps. We are talking about a whole other level of analysis here. The kind of thing that used to be only for, elite athletes in super expensive medical labs. What if that little device on your wrist could see the tiniest changes in your stride, the subtle shifts in your balance? What could that tell you about your health?
And that unique rhythm, the way you walk, it has a name. It's called your gait. And it's basically a fingerprint for your health. Think of it like a walking signature that's totally unique to you. Just like a doctor checks your heart rate, we're now learning how to read your gait to get a snapshot of your overall well-being. It's a powerful new vital sign that's been hiding in plain sight this whole time.
So if gait is so important, you might be wondering, why isn't it as common as checking your blood pressure? Well, the answer comes down to a classic problem. It's always been a trade-off between getting super accurate data and actually being able to get that data in your daily life. Until now, you really could only have one or the other.
I want you to picture this for a second. A high-tech laboratory filled with special force plates on the floor, motion capture cameras all around, and a whole team of scientists analyzing every tiny detail of your stride. That's traditional gait analysis. It's incredibly precise for sure, but it's a universe away from our normal, everyday lives.
So you see the dilemma, right? On one hand, you have the gold standard, the lab. It's super accurate, but you can't exactly pack it up and take it with you on your morning walk. Then, on the other hand, you've got your smartphone. It's always with you, which is great, but its accuracy completely depends on where you put it. Is it in your front pocket, your back pocket, your bag? That makes it pretty inconsistent for tracking things over time. But what if there's a third option? What if the key to unlocking all this amazing gait data has been right there on our wrists this whole time? This is where the smartwatch comes in, the unlikely hero of this story. You know, the real beauty of the smartwatch is its consistency. It's simple, right? It's always there in the exact same spot, capturing the movement of every single arm swing when you walk. And this constant, reliable stream of data, well, that turns out to be the secret to its power. So how does the magic actually happen? It's basically a three-step dance between you, your watch, and a really smart AI. First, your watch's sensors capture the raw data, the rhythm of your arm swing. Then, you just provide one little piece of the puzzle, your height. And finally, the AI model takes all of that and translates it into this incredibly rich understanding of how you walk. Okay, so what kind of insights can this actually unlock? Let's start with the most intuitive one, gait speed. It's really just a simple measure of how fast you walk, but it turns out to be a surprisingly powerful signal for your overall health. But believe me, it gets even more interesting. The AI can also measure something called your double support time. That's the teeny tiny split second in your walking cycle when both of your feet are on the ground at the same time. It's a critical moment for stability, and it's a very subtle detail that can be an early warning sign for balance issues down the line. And then, of course, there's step length, the distance you cover with each stride. And get this, the AI can figure this out just from the motion of your wrist. It's kind of amazing when you think about it. It's like having that high-tech gait lab we talked about, but shrunk down to fit right on your arm. So how in the world does a watch on your wrist know how long your legs are? What's the secret sauce? Well, it's that one simple piece of information you provide, your height. That turns out to be the crucial missing link that lets the AI accurately translate the swing of your arm into a precise measurement of your stride. Now, all of this sounds really impressive, but the big question is, does it actually hold up in the real world? To answer that, researchers put this technology through its paces in a really comprehensive study. And we're not talking about a small test with a handful of people. No, this study included 246 participants, a really diverse group of people, to make sure it represented the real world. And the amount of data they collected? It's just mind-boggling. The AI was trained and tested on nearly 70,000 individual walking segments. That's a mountain of data, and it's exactly what makes the AI model so smart and so powerful. The researchers didn't just test this in perfect, ideal conditions either. They really pushed it to its limits. They had people walk at their own pace, walk really fast, and they even had them wear a knee brace to simulate an uneven, asymmetric gait. They wanted to know if this AI could handle the messy reality of how humans actually move. So, after all of that rigorous testing, what did they find? Well, the results were pretty remarkable, and honestly, they have the potential to completely change how we think about our personal health. The main event, The real question on everyone's mind was, how does the smartwatch stack up against the smartphone? Could a device on your wrist really be as accurate as the one we've been carrying in our pockets? And when it came down to accuracy, wow, it was a dead heat. The smartwatch was just as accurate as the smartphone. The difference between them was so tiny that it was actually statistically insignificant. It was a tie. So what's the bottom line here? It's pretty clear. The smartwatch is a totally legitimate, scientifically valid tool for analyzing your gait. It's just as accurate as a smartphone, and with that one simple addition of your height, it can unlock a whole new world of personal health insights.
Look, this is more than just a cool technological breakthrough. It's really a glimpse into the future of our health. So let's talk about what this actually means for you.
Imagine if you could catch a potential health problem before it ever becomes a real crisis. Or what if your rehab or your fitness plan was perfectly tailored to the unique way that you move? That's the promise of this technology. It's all about proactive, personalized healthcare, and it's sitting right there on your wrist.
We are just scratching the surface of what's possible here. As our devices get smarter and smarter, what other aspects of our health are they going to unlock? The future of personal medicine is arriving, and it's more accessible than ever before. So the real question is, what secrets will your watch reveal about you?
All right, let's talk about something that could totally change the game for AI in China. It all comes down to one thing: data. And there's this huge new data set called DanQing that's about to give Chinese language models a massive power-up. But before we get into that, let me ask you something. What do you think is the biggest roadblock for AI that isn't English-based? You might think it's, the fancy algorithms or the processing power, right? Nope. The real bottleneck, it's the data. Think about it like this. An AI model is only as good as its data diet. Seriously, just like with people, what you feed it completely changes how it performs. And for a long, long time, the diet for non-English AI has been, well, let's just say it's been pretty sparse. So how do these powerful AIs learn anyway? Well, at a basic level, it's something called vision language pre-training. They basically just look at millions or even billions of pictures from the internet, and each picture has a little text description with it. By connecting the words to what's in the picture over and over again, they start to build this incredible understanding of, well, everything.
And this right here, this shows you the problem perfectly. Look at the big English data sets, LION and Koyo. We're talking hundreds of millions of data pairs. Now look at the main Chinese ones, like Wukong and Zero. Yeah, they're big, but they're smaller. And here's the kicker. They're from 2022. In the AI world, that's ancient history. And that has been a huge, huge problem for developing AI in China.
Okay, so that's the problem. And this is the solution. Enter the hero of our story, the DanQing dataset. It was built from the ground up to tackle this exact issue and give Chinese AI the modern fuel it's been starving for. And the name, DanQing, it's actually really cool. It's a traditional term for Chinese painting, and that just fits perfectly, right? Because the goal wasn't just to make something big, but something full of cultural and artistic detail. And when we say big, we mean big. We're talking 100 million high-quality image-text pairs. Just imagine that. It's like an enormous digital library for an AI to study. But here's the real game changer, the most important part. This data isn't old. It was collected from the web in 2024 and 2025. What does that mean? It means any AI trained on this stuff understands the world today, not the world from a few years back. That's a massive difference. So you're probably wondering, how on earth did they get such high-quality data? Well, they didn't just scoop it all up. They basically put it through this incredibly tough digital boot camp to weed out all the junk and keep only the absolute best stuff. And this is how they did it. It was this intense four-step process. First, they did a rough, broad filter to get rid of the obvious garbage. Then, they cleaned up the text. After that, they filtered the images themselves. And the final, crucial step, making absolutely sure the picture and the text actually matched up. And get this, to end up with their 100 million pairs, they didn't start with 100 million. They started with over 1 billion raw pairs they found on the web. 1 billion. They had to comb through that absolute mountain of data just to find the gold. This chart right here, wow, it really tells the whole story. After all that work, they threw out 90% of what they started with. 90%! Only the top 10%, the absolute cream of the crop, made the cut for the final dataset. Now that's what I call being picky. Okay, so great. They've got this super clean, super modern dataset. But so what?
Does it actually matter? The proof is in the pudding, right? You've got to train a model on it and see what happens.
And yeah, the results speak for themselves. There's this test called zero-shot classification. It's a fancy way of saying you ask the AI to identify stuff it's never seen before. And the model trained on DanQing, it consistently beat the models trained on the older datasets. Now those numbers might look pretty close to you, but trust me, in the world of AI, that little edge is a giant leap.
But that's not even the coolest part. I mean, doing well on standard tests is one thing. But what about the real test? Can it understand brand new things? Stuff from 2024 and 2025 that literally didn't exist when the old datasets were made. Okay, this is just wild. Look at this. They asked the models to identify the Xiaomi SU7. That's a new electric car that just came out. The model trained on old data was basically clueless, a confidence score of like 13%. But the DanQing model, a staggering 92.3%. It's not just smart, it's current. It actually knows what's going on in the world right now. So you see, this is so much bigger than just getting a better score on a test. What we're looking at here is the creation of a whole new foundation for AI, one that's actually in sync with the modern world and its culture. So let's just recap the DanQing advantage. First, the text quality is way higher, which means the AI understands things better. Second, the topics are more balanced, which helps cut down on bias. Third, it's built to scale up, so it'll work great with even bigger models down the road. And finally, the most important point, it is completely up to date. It knows our world. And you know what? The best part is, the team behind this isn't locking it away. They're making the whole thing open source. They're giving it to the community. In their own words, they want to give everyone a robust foundation to speed up research. That's just a massive gift to the entire AI field. Which really leaves us with one big final question to think about. DanQing is a huge leap for AI in China, for sure. But as AI goes truly global, who's going to do this incredibly important work for all the other languages and cultures out there? Who's going to build the data for the rest of the world? All right, today we're jumping into some research that could completely change the game for how we build AI. The big idea? Teaching a machine to understand the world not by feeding it textbooks, but just by letting it watch and watch and watch countless hours of raw, unlabeled video. Let's get into it. So let's kick things off with a huge question, maybe the question. How do you actually get an AI to, understand what's going on in the world? How does it grasp cause and effect, motion, why things happen just by watching? Honestly, this is one of the biggest hurdles in the entire field. The way we used to do this was with labeled data. That's where people, actual humans, have to sit there and painstakingly tag everything in a video. This is a person walking. This is a car turning left. As you can see on the left here, that whole process is super slow, it's wildly expensive, and it's just so limited. But the new frontier, what we're talking about today, is on the right. Learning from raw video, that gigantic, unlabeled ocean of content that's already online. It's fast, it's scalable, it's diverse, and it lets the AI figure things out all on its own. So, what's this all really about? Well, it boils down to one critical thing: prediction. See, for an AI to be truly intelligent, to plan, to act, to do useful stuff, it has to be able to predict what's going to happen next. It has to understand the consequences of an action. And that brings us to the hero of our story today, the Latent Action Model, or LAM for short. The key word here is latent, which just means hidden. A LAM watches a video, it sees a scene change from one moment to the next, and it figures out the invisible action that must have caused that change. It's basically teaching itself the physics and the logic of the world from scratch. Okay, so how does this thing actually work? It's a really slick two-step dance. First, it infers. It looks at a before frame and an after frame and asks itself, okay, what's the one action that gets me from point A to point B? It's working backward, from the effect to the cause. Then, to prove it actually learned something, it predicts. It takes that original frame, applies the action it just figured out, and tries to perfectly recreate the after frame. If the two match up, boom, it's learned something real about the world.
But wait a second. There's a catch, right? There's a really clever way the AI could, cheat. What if that hidden action it learns is really just a super compressed copy of the next frame? If that happens, it's not learning about the action at all, it's just memorizing the answer. And that's totally useless for making new predictions. So how do you stop it from cheating the test?
Well, the researchers came up with 3 really smart tricks to keep the model honest. First is something called sparsity, which basically forces the action to be represented by just a few really important numbers. No fluff. Then there's noise addition. Think of it like adding a little bit of static to a phone call. It forces the model to learn the core message instead of getting bogged down in tiny details. And finally, there's discretization, which is like giving the model a fixed dictionary of possible actions to choose from. All three of these stop the AI from just copying the homework and force it to learn the real lesson.
All right, so this all sounds great in a controlled lab setting. But this is where things get really exciting and really, really hard. They took this model and threw it into the wild. We're talking about the messy, chaotic, unpredictable world of internet videos. And this slide just lays it out perfectly, right? On the left, you've got your typical lab data. A robot arm, maybe a video game. Everything is consistent, the actions are clear, there's not a lot of background noise. On the right, that's YouTube. That's the real world. There's no single character or body, the actions are all over the place, and the environment is just pure chaos.
And this quote from the paper, man, it just paints such a vivid picture of the challenge. The model has to learn to understand everything from cars driving by to people dancing to something as incredibly detailed as fingers forming chords on a guitar. It's just a monumental leap in complexity.
Okay, so we've set the stage. We know the challenge is massive. The big question is, did it work? How did this model actually do when it was faced with all this incredibly complex, in-the-wild data?
So first up, let's look at one of the older ways of doing things, that discrete method with a fixed dictionary of actions. It's trying to predict a person entering a room. And, well, you can see the results is kind of blurry, indistinct. It's almost like a ghost. The model is really struggling to capture that fluid, complex motion with its limited vocabulary. But now, check this out. Wow. This is the prediction from the new model, the one using that sparsity trick. It's unbelievably clear. It perfectly predicts the person entering the room and walking across the scene. I mean, the difference is just night and day. This is a massive leap forward.
So the big takeaway here, the real insight, is this. Using a more flexible, continuous way to describe actions, while still keeping it in check with tricks like sparsity or noise, is just way, way better for understanding the complexity of the real world than trying to force everything into a rigid, predefined dictionary.
But it gets even cooler. This is where my mind was kind of blown. The researchers wanted to see if the model was learning abstract ideas. So first step, they showed it this video of a person walking to the left. And the model did its thing. It figured out the hidden, latent action for move left.
Okay, next, they took that learned action and showed the model a totally different video. This time, it's just a simple purple ball flying through the air. These two videos have basically nothing in common. Different objects, different backgrounds, different motion.
So what do you think is going to happen when you take the idea of walking left that it learned from a person and apply it to a completely different object like this flying ball? You guessed it. It works. It absolutely works. The ball's original flight path just stops, and instead it starts moving to the left, perfectly mimicking the motion pattern from that first video. This is huge. It proves the model didn't just learn a person walking. It learned the abstract, general, transferable concept of movement to the left.
And the reason this works is, well, it's kind of a beautiful accident of the experimental design. Because the model was trained on all these diverse videos that didn't have a single consistent body or character, it was forced to learn a much more universal truth. It learns that actions are just transformations. They're changes that happen in a certain part of the screen relative to the camera. And that makes the actions it learns incredibly powerful and general.
Okay, this is all incredibly cool science. But what's the point? What can you actually do with this? This isn't just an academic toy. The whole goal is to build AIs that can actually interact with the world. And to do that, you need a universal language for actions.
And here's how you bridge that gap, from just understanding the world to actually controlling it. First, you train a tiny little controller that acts as a translator. Its only job is to learn how to map a simple robot command, like move your arm forward, to the rich, complex, latent action that the big AI has already learned from watching videos. Once you have that translator, you can use it to give commands to the powerful world model, letting it plan out complex steps to solve real tasks.
And this is the mic drop moment, right here on this table. Look at this result. The LLM model, the one trained only on messy, unlabeled YouTube videos, was able to perform complicated robotics planning tasks almost as well as a standard model that was trained on perfect, hand-labeled, task-specific data. Think about that. That is a massive, massive step toward building general-purpose AI that can learn on its own.
And that leaves us with one final, absolutely massive thought to chew on.
What this research really shows is that it might be possible for an AI to learn the fundamental language of action just by passively watching the world go by. So if it can learn from every video ever uploaded, if it can build an intuition for physics, for cause and effect, for human intention, what on earth will it be able to do next?
Welcome to The Explainer. Today, we're jumping into a really cool new paper from Sakana AI. They're tackling one of the biggest headaches in AI right now. It's surprisingly short attention span. So let's get right into it. We've all seen AI do these incredible things, right? It can write poetry, it can generate code, the whole shebang. But have you ever tried to give it a 200-page legal contract or maybe a super long chat history? Suddenly, its performance just falls off a cliff. It gets lost, it forgets really important details, and it just fails at the very things we need it for. This whole issue has a name. It's called the long context problem. And honestly, it's one of the biggest hurdles holding AI back today. You can almost think of it like the model has a very, very expensive form of amnesia. The longer it reads, the more it forgets, which makes trying to reason over long documents practically impossible. Okay, so you might be thinking, well, why don't we just train the models on longer and longer stuff? And that's the obvious question, right? But it turns out it's incredibly hard to do. There are two huge reasons. First, just finding enough good, clean, really long documents is a massive challenge in itself. And second, the cost. The compute cost is, and I'm quoting the researchers here, brutally expensive. That's because the attention mechanism that makes these things tick gets exponentially more demanding the longer the text is. Because of those crazy costs, the real goal, kind of the holy grail here, isn't just longer training. It's something called length generalization. The idea is, can you train a model on a relatively short piece of text, say 4,000 words, but then have it work perfectly fine on a document that's 10 times longer, without ever having to retrain? But here's the tough reality for most models out there today. When you try to push them past the length they were trained on, they don't just get a little bit worse. They completely break. The text they start spitting out is just incoherent nonsense. So what's the culprit? What's causing this catastrophic AI amnesia? Well, the investigation leads us to this really crucial part of the AI's architecture. And it's something that creates this fascinating paradox. It's a component that is at the same time incredibly helpful, but also a major, major hindrance. The main suspect is a thing called positional embeddings, or PEs for short. You see, a transformer model on its own just sees text as a big jumbled bag of words. It has no idea what order they're in. PEs are what tell the model the sequence. Without them, man eats fish and fish eats man would look exactly the same to the AI. And the most popular kind today is called ROPE. And here is where the paradox kicks in. During training, these PEs like ROPE are fantastic. They're like giving the model a huge head start. It gets this built-in understanding of word order, which helps it learn the structure of language way faster and much more effectively than models that are trained without them. The researchers at Sakana AI put it perfectly in their paper. They said, quote, PEs are a key component for effective LM training, but are also a fundamental barrier to long context generalization. So the very thing that makes the model so smart and efficient during training is also the very thing that breaks it later on. It's a classic catch-22. So let's dig in a little deeper. How does this super helpful tool turn into a major roadblock when we really start to push the limits of what these models can read? Well, the problem is that these positional signals, they're based on some pretty complex math, rotations to be specific. And when you feed the model a document that's way longer than anything it's ever seen before, those rotations go into completely uncharted territory. The model has just never seen a position number that high. And that ends up warping its internal attention mechanism, totally confusing it. Now, of course, people have tried to come up with clever workarounds for this. They've tried tricks to scale or compress the PEs to keep them in a range the model recognizes, and it kind of works. It stops the model from totally breaking, but it creates this sneaky new problem. The model just starts ignoring information that's far away in the text. So it can still form coherent sentences, but it loses that critical ability to remember something from page 1 when it's on page 100. And this is where that breakthrough idea from Sakana AI comes in. They solve this whole paradox with a solution that is almost, well, it's deceptive in just how simple it is. The researchers asked this one brilliant, fundamental question. They said, what if we could use these positional embeddings to get all their amazing training benefits and then just get rid of them before they have a chance to cause problems?
The core concept here, and it's a great analogy, is to think of positional embeddings like scaffolding on a skyscraper. You absolutely need that scaffolding to build the structure correctly, to put everything in the right place efficiently. But once the building is finished, once it can stand on its own, you take the scaffolding down.
And this insight leads to their 3-step process, which they call DroPE. Step 1. You pre-train the model just like normal, with rope, letting it do its job and build a really strong foundation. Step 2, and this is the magic trick, after that training is done, you just drop the PEs. You just take them out. And then step 3, you run a very short recalibration phase, basically training the model for just a tiny bit longer so it can adjust to working without its scaffolding. And what you get from this simple procedure is a model that keeps all of its original performance on the tasks it was already good at, but now it can suddenly handle these incredibly long documents without any issue at all. It achieves true length generalization.
Okay, so the idea sounds great in theory, right? But does it actually work in the real world? Well, let's look at the results because they are pretty staggering.
That final recalibration step, that little adjustment at the end, it's astonishingly efficient. It is so cheap, you can just do it at the very end of a model's normal training run for basically no extra cost. And think about this. With just that tiny bit of extra fine-tuning, the model regains over 95% of its performance on the original, shorter tasks. So you lose practically nothing by taking the scaffolding away. To put that cost into perspective, when they applied this method to a huge model, Llama 2 7B, the whole recalibration phase only required 0.5% of the original training compute. That makes this an incredibly practical solution that you could apply to even the biggest models out there.
But here's the real kicker. They tested this on Longbench, which is a key benchmark for these long context tasks. And DroPE didn't just outperform the other methods, it blew them out of the water. It improved the base model score by over 10 times. That's not just a small improvement, that is a massive leap forward.
So, what's the big takeaway here? It's that by treating a component we thought was essential as just temporary scaffolding, we can unlock a capability that has been holding AI models back for years. DroPE gives us a simple, cheap, and incredibly effective path to true long context understanding. And this all leaves us with a really provocative thought, one that could shape the future of how we build these things. It just makes you wonder, what other parts of today's AI that we think are absolutely essential are actually just scaffolding that we haven't learned how to remove yet? Thank you for joining this explainer.